You can have a gravitational dipole, an electric dipole, or a magnetic dipole, which can be either a bar magnet or a loop of current. Let's compare them. For the gravitational dipole, if we consider this to have mass m, and this, because of buoyancy, negative m, and they're separated by a distance d, the torque on this thing would be 2 times d over 2 times mg times the sine of the angle between the dipole direction, helium to lead, and the gravitational field direction. Similarly, an electric dipole in an electric field. In physics, chemistry is backwards. In physics, the electric dipole P, which is Q times D, points from negative to positive. So the angle between P and E could be theta there, and the torque turns out to be P cross E, which means its magnitude is P times E times sine of theta. Likewise, a magnetic dipole moment is mu. So the torque would be mu cross B, and its magnitude would be mu B sine theta, same theta as before. And likewise with an electric current. A magnet, they'd have to just tell you its dipole moment. For a current, you know that the mu is number of turns times the current times the area. In fact, the area vector. So in the case of a circular loop, that would be I times pi r squared. Now, what about energy? There's potential energy involved in the orientation of the dipole. Low energy would be the lead weight hanging down. That's where it wants to settle, and the helium pointing straight up. Now, it turns out the formula for the energy is minus the dipole dotted with the field. The gravitational dipole, you could say, is mass times distance. Let's see, not quite sure what to call it. I'll call it big D dot G. So that would equal minus, the dipole would be m times d, and G is our 9.8 here on Earth, and we would have the cosine of the angle. So what does that mean? It means the low energy state would be when this cosine is 1. And when it's hanging straight down, the gravitational potential energy would be negative mgd. And you're going to reverse that when you lift the mass up. Now, notice that the change in energy, if you flip it over, is twice this amount. So it would actually be 2 mdg to flip this thing. That's the difference in energy between the low energy state and the high energy state. Similarly, for the electric dipole, the energy is minus P dot E. So that's minus P E cosine theta. And the P is Q times D. Likewise, the magnetic one, and you will need this for further magnetism tricks like the MRI. The energy would be minus mu dot B, which would be minus mu B cosine theta. And the difference in energy required to flip it over would be 2 mu B, because you go from negative 1 to positive 1 with a difference of 2. So there you have it.